So the next thing is to look at these surfaces in 3 dimensions, which are more complicated than planes. So we've seen planes which are sort of 2-dimensional objects living in 3-dimensional space. Those are the simplest kind of surfaces. So now we're going to get a little funkier. So what's the next easiest type of surface that we can make? Just take a known graph from 2 dimensions and then extend it into 3 dimensions. For example, the graph of y equals x squared. Now I'm going to ask you what this looks like, but keep in mind, we want to talk about what the graph looks like in 3 dimensions. So you've got x, y, z axes. So what happens? So what does this look like? So wherever we look, we've got the graph y equals x squared. So how do we account for the z value? Well, y equals x squared for any z value. Z equals 1, z equals 2, blah, blah, blah. So one way to imagine this is that we're going to take a slice at every single z value. So at any z value, you get a parabola, y equals x squared. So you could call it a slice, you could call it a cross-section. We'll learn some more official terminology later. And naturally, 3-dimensional graphs are typically more complicated than this, as we will see. So for example, how do we make the graph x squared plus y squared equals 4? So in 2 dimensions, this is a circle of radius 2. Around the origin, right. So how do we make this in 3 dimensions? Right. So again, imagine that you have your x-axis and your y-axis. So in that xy plane, you would just have a circle. My drawing skills are awesome. All right. There we go, something like that. And again, remember, we're looking at it from a sort of like an angled perspective. Okay. But now we want to add this 3rd dimension. So what happens? Well, basically, at every z value, you've got a circle. So it's like a stack of circles. So you wind up, if you want to draw them all in, you wind up with a cylinder. So with the first surface, I mentioned slices or cross-sections. So how do you take a cross-section? So if you've ever had a science lab class, you've actually done this. Or actually, if you've ever cut a slice of meat, you've done this. Or cut a slice of anything. Imagine having a carrot or something, you cut off a thin slice. So how can we cut off a thin slice? Or just imagine the knife chopping through at a certain z value. So you could either say I'm going to take a knife, chop through a z value, or mathematically what we say is we're going to take a plane and slice it through. So if you like, you could imagine that there's some plane that cuts through the surface. Let's just say this is the plane where z equals 1. So we talked about the equations of simple planes before. So the plane z equals 1, it's like the xy axis, but it's sitting up 1 unit. Okay, so if you take that plane and intersect it with your surface, you get the part of your surface where z equals 1. And what we said before is that, well, it's always going to be the case that x squared plus y squared equals 4. So when we intersect that plane with our surface, what we'll get is that circle.
So in this case, isa is not the constant.
Okay. So let's look at a surface that's slightly more complicated than this. Let's talk about the graph z equals x squared plus y squared. So what does that look like? So the first thing I should mention is don't be confused by the fact that there are these like sort of 4 little hammock points, that's merely a function of where the graph is cut off the range of graphing. It's sort of, think of it more as like an open eggshell. Okay. So, and you can see the range of values that I've graphed just based on the box. So this thing just continues up forever, if you like. Okay. So this graph actually comes from the rotation of a parabola. It's called the paraboloid. It's a 3-dimensional parabola, if you like. Okay. So what does the equation have to do with the graph? How are they connected? All right, let's think about a couple different ways. So first of all, when z is a constant, what's happening? So for z equals 1, z equals 2, whatever, as we saw previously, we're in a plane parallel to the xy plane. And let's look at the equation for a second. When z equals 0, you get x squared plus y squared equals 0. Well, that just means that they both have to be 0. Basically, I have a circle of radius 0. That's a point. For z equals some constant, you get a circle. And for bigger z value, you get a circle with a bigger radius. So if you think about it on the graph, you've got a point, then you've got a circle, a bigger circle, bigger circle. Higher values of z give you a larger circle. Okay. And once again, you could mathematically generate these circles by intersecting your surface with a plane. And that plane will intersect at a circle. All right, now we're going to do something different. We're going to say, what about if we let y be a constant? So when y is a constant, first let's look at the surface. So on the surface, when y is a constant, the y value isn't changing, and we know we're going to sort of, excuse me, we're going to be looking at the xz perspective, or an xz plane. So what does that give us? Well, that actually gives you these lines that are already drawn in. You get this. And notice that that's what would happen if you took this plane. Wait a second. Try to keep it in perspective, so to speak. Okay. So there's the plane, approximately, say, y equals 0 or y equals -1, something like that. If you intersect that with your surface, what you get is this line. And other planes, y equals 1, y equals 2, y equals -1, y equals -2, you can see, because the software has kind of already graphed it, you'll get these curves. So what are these curves? Well, to figure out precisely what they are, we can look at the equation. So let's look at the equation. Z equals x squared plus y. If y is a constant, what do you get? You get z equals x squared, and if y is a constant, then you get c squared for some constant. So it's just a parabola plus it's a parabola where you've got plus a constant on the end. It would be a shift, exactly. Okay.
So in a case like that,
So this is what happens if we look at y being a constant. What about if we look at x being a constant? So x being a constant, so for example, x equals -1 means we're here. So your plane would cut through something like that. And what lines does this generate? Now, it's a little tough to see from this perspective, but you can sort of, I think, imagine it's going to follow this path, then it's going to go down, then it's going to come up on the other side. Oops. Okay. And if you want to understand algebraically what that is, again, you'd say z equals c squared plus y squared. So when x is some constant, once again you get a parabola, but where z is a function of y. And again, the software used to make these has actually already drawn in all these lines for your visual convenience. Okay. So now a bit of terminology. The last thing we just talked about, where we said let x equal a constant and see what that graph looks like, that's called an x-trace. And so it lives in a plane parallel to the YZ plane. And that's what's actually graphed there right now. Similarly, a cross-section with y constant is called a y-trace, and it lives in a plane parallel to the xz plane. And a cross-section with z equals a constant is a z-trace that lives in a plane parallel to the that's a typo. Parallel to the xy plane. Okay. So in this example, x traces and y traces are parabolas, and z traces are circles. Another way to think about this is to imagine that you take all the x traces, or all the y traces, or all the z traces, and stack them together to build the surface. So perhaps it's easiest to think of in the case of the z traces. So in the z trace, you get a circle, a circle, a circle, a circle, a circle, and you stack them all on top of each other, and you wind up with this parabola. Now, paraboloid, excuse me. And when I'm talking about this, I'm talking about the graphs. I'm talking about this in an informal way. Informally, we're thinking of how can we visually analyze this three-dimensional surface. So one way is to think of all these z traces, which are circles, stacked up in this way that gives a paraboloid. Now another way to think about it would be to think about the y traces. So we could take all the y traces, where you've got this parabola, this parabola, this parabola, this parabola, this parabola, this parabola, and then of course also the parabolas on the back side as well. And then you could stack those together in order. And then in a sense, that's also another way to build the surface. Okay, so one more fun surface. Okay. So x squared over 4 plus y squared over 9 plus z squared over 16 equals 1. What does this kind of look like the equation of from 2 dimensions? An ellipse. So this is the extension of an ellipse into 3 dimensions. And that's called an ellipsoid. And it looks like that. Basically, it looks like an egg, more or less. Okay. So let's talk about what the traces are. So x traces, y traces, z traces. So an x trace means you're taking x to be constant. So we're using this plane. So when we cut that through, what are we getting? We're getting this, and then it runs up the backside. So what shape is that? Yeah, it's clearly some kind of circly, ovally kind of thing, and you can kind of guess from the fact there's a three-dimensional ellipse, that shape is an ellipse. Okay. What about y traces? What about z traces? So you can use your cleverness either from looking at the equation, or from looking at the shape, or from looking at the name of the shape, to see that each of these is actually going to be the same thing. So y trace will come from cutting a plane, running a plane through that looks like this. and you're going to get one of these. So you're going to get all these curves. So once again, you get an ellipse. Now you can also, and the same thing for z. Okay. Now, of course, that's using the graph. What about from the equation? Let's look at what an x-trace would be. So an x-trace would give you c squared over 4 plus y squared over 9 plus z squared over 16 equals 1. So what is this? So how can we figure this out? Well, at this point, this is the algebraic approach. You just have to do some algebra. So what you do is you get y squared over 9 plus z squared over 16 equals 1 minus c squared over 4. And now you have y squared over 9 plus z squared over 16 equals some number, but some number that's smaller than 1. So what you could do is multiply both sides by some constant so that on the right side you get 1 again. And now you just have y squared times some constant plus z squared times some constant equals 1, and that's going to be an ellipse. So you could actually work it out specifically with the algebra, but we're not, at this point, we don't need that. We just want to know, generally speaking, what is this going to be. So that's what you get. And so notice that as c changes, it changes the constants involved in the ellipse. And again, you can see this on the picture. You can see that for x traces or for y traces, as you change where you're taking your slice, constant equals 1, 2, 3, whatever, you get an ellipse of a different shape or a different size. Okay. So next, for your entertainment, I'm going to show you a whole family of surfaces. The ones that I've shown you so far are examples of quadric surfaces. So these are surfaces whose equations can be made from x, y, z, x squared, y squared, z squared, and then constants. There we go. Okay. So we've got the ellipsoid, which we already looked at, and then here are some other ones. So we've got an elliptic paraboloid, where it's kind of like a paraboloid, except the z traces are ellipses instead of circles. And the hyperbolic paraboloid is pretty funky. If you take a flat cross section, if you take a z trace, you get a hyperbola. Notice that if you run a flat plane through, like z equals 1, z equals 2, the graph will actually be in two pieces.
What was the last one you said?
The graph will actually be, if you take a z trace, the z trace actually is not connected. It's in two pieces. Right. So these are just some fun possibilities. Okay.
I noticed that you call them horizontal traces or vertical traces.
So what we've seen so far are just examples of all different kinds of surfaces in 3 dimensions, where you simply have some equation in terms of x, y, and z. What we're going to look at now is we're going to talk about functions. So in this case, as I alluded to previously, we're going to talk about z as a function of x and y. So in this case, it's going to be useful to always think of z as being on the vertical axis and z being the function value. And that's the realm that we're going to enter now. Okay, so plugging in values for x and y yields a function value z. Notice that that certainly doesn't have to be the case, and with these surfaces, that's not the case at all. Z is not a function of x or y for several of these. Actually, for which ones is it a function and which ones is it not a function? So the ellipsoid, is that z being a function of x and y? No. Right. Not exactly. You get two z values. What about the elliptic paraboloid? That one is a function. And in fact, you can see it in the expression because you can just multiply by c and solve for z. Okay. So right now we're going to spend some time focusing on functions. Okay. So here's a function. Z equals the square root of x plus y. So first of all, let's find f of 4 comma 5, and let's find the domain. Okay. So f of 4 comma 5, this is the simplest thing you'll do. You just plug it in. Okay. Next, find the domain. Well, what's going to tell us about the domain of this function? Yeah, there's a square root. So for the domain, we're going to need x plus y to be at least 0. And so that's the domain. Yes. So notice that previously in 2 dimensions, what was your variable? Your variable was just x. So you got to say things in terms of x. X is bigger than this, x is smaller than this, whatever. But now you've got 2 variables. So in most cases, except in the simplest cases, in most cases, your domain is going to be described in terms of both x and y, because both x and y are your variables. So now, hypothetically, if we wanted to draw what this domain looked like, how would you do that? Yeah. Okay. So what we're doing here is we're graphing an inequality. So first you graph the equality. So x plus y equals 0, which is the same as y equals. So another way to think of this is that y is greater than or equal to negative x. Right. So you draw it like this. And then we want greater than. So it's that. So that's the domain of the function. Now, to help us think more about this, let's talk about these functions as graphs. Okay. So, first of all, what shape does this look like? Okay. Half a sphere. So, remember that a lot of the time you're going to have to change your change your terminology from the names of 2-dimensional shapes to the names of 3-dimensional shapes. So this is not part of a circle; it's part of a sphere. Okay. So it's top part of a sphere. Okay. So now what's the? So you know what? That's actually true. Great. So what's the function? So let's see, what can we learn about this sphere or hemisphere? First of all, what's the center of the sphere? Okay. So this is, let's say this is z, this is x, and this is y. So the center looks like it's at x equals 0, And then over here, y equals 0. And then what about z? Also, turns out it's also z equals 0. Made it easy. So the center is the origin. 0, 0, 0. Okay, now what's the radius? Yeah. So if you're using the software live, you could manipulate it and look at it straight from the side, and you'd see that the radius is exactly 3. So that gives us the three-dimensional equation for a sphere. X squared plus y squared plus z squared equals 3 squared. Which is the natural extension of the equation of a circle. Okay. Now we want to write it as a function, because we're talking about functions. So solve for z, and you get z equals the square root of 9 minus x squared minus y squared. Now, of course, if it was a sphere, it would be a top half and a bottom half, plus and minus, but we're just talking about the top half, so it's just positive. Okay, what's the domain of the function?
Negative x squared minus y squared has to be greater than or equal to circle.
Let's just write it down simply first. So very simply, 9 minus x squared minus y squared is greater than or equal to 0. So write the simple thing first, and now you can play with it. So this tells you that x squared plus y squared has to be less than or equal to 9. So in that case, I flip directions. If you like, you could also say 9 is greater than or equal to x squared plus y squared. Either way. Okay. So what is the domain? The domain is a circle. Or, well, the domain is a disk. It's a filled-in circle, if you like. So in the graph as it's drawn, the domain is that region right there. In the xy plane itself, that's the domain. And then notice that every single point in the domain has a function value. And that function value lives either above or below that point in the domain. This is very much like the two-dimensional case, where we could say, for example, let's see. If you think about the square root function, the domain is that part of the x-axis, and then every value, in this case, is above, but it could be either above or below. The difference is that instead of the domain being a line, because you just have one variable x, the domain, instead of being on a line, the domain is now in the plane, because you have two variables x and y. So it's a part of the xy plane. And then values are either above or below based on if z is positive or negative. So for example, based on this equation, we know that the domain is that. So notice that the domain is two-dimensional. It's in x and y. And if you take that disk, that's the disk over which we're going to build our dome. And the heights of the dome are represented by z-values. So question. Is this the same as x from -3 to 3 and y from -3 to 3? Is that the same thing?
Oh, yeah. I believe so. You need a combination.
Well, the region of x from -3 to 3 and y from -3 to 3, if I just told you to draw that from scratch, what would that look like? It would look like a square, exactly. So how do we describe this region in a different way is something that we're actually going to look at later. Aside from just giving that one equation, there are other ways to do it, and we're gonna get to that later. Next. So we're actually going to think more about z-traces now, but in a different kind of way. So let me tell you a story. Before there was all this mathematical software which could render these beautiful images indicating depth with shadows and lines, people needed ways to visualize three-dimensional objects using two-dimensional paper, making an image on that paper. So the most common technique was developed by map makers who wanted to represent mountains and valleys and make these topographical maps. So they drew a curve to show every point which was at the same height. So in a second we're going to look at a mountain and its map. Let's get that up here. There you go. So on the left you've got the mountain, and on the right you've got the map. So what does the map show? Well, that map is called the contour map, and the lines are called level curves. Moving along a level curve means moving along the same height. Height, if you think of it topographically, or more generally speaking, same function value. So notice that what we're saying is that along each of those lines, z has the same value. So in other words, these are just z-traces. Now in this case, z has a special place because z is now a function of x and y. So z-traces are now called level curves, and they get a special role, as we're going to see. So notice that, so again, moving along a curve means you're walking along the same height, and then moving from one curve to another curve means your height has changed. Height, or more generally, function value. So let's take a look where I mean this more generally. So here we've got a map showing temperatures. So in this case, x and y are latitude and longitude, and then your function value is the temperature. So in this case, your contour lines represent a constant temperature, or the same temperature. And in this case, they're called, and in meteorology, they're actually called isothermals. So iso means the same, and therm means temperature. And if you can see in the background there, there's a map of North America. So let's take a look at, let's see, Florida. So over here we got Florida. Now it looks like that that level curve of 80 degrees runs about right through the middle of Florida. So let's call that Orlando. So on the day represented by this contour map, it was 80 degrees in Orlando. What would you say the temperature is in Miami?
Where's Miami?
Miami is in the southern tip of Florida.
85.
Right. So Miami would be right there.
80.
A little bit more than 80. Everything within this line is 80.
Maybe like 84. If this is like a topographical, then that's 80. Because each slice represents, it's like looking from above. Each slice represents like 84.
So we know that this is 8. So we know that everything there is 80 degrees. But what other temperatures what other places and temperatures do we know? We know that everything over here is 70. That's cutting through about Georgia or something. And then over here is 90 degrees. So what do you think it is in Miami? It's above 80. It's about, I don't know, 83, 84, something like that.
Professor, the topographical map, I mean, I used to walk them in the army. The topographical maps each represent a slice.
Right. It's important to keep in mind that this represents something, the temperature is changing probably continuously. So there's a place where it's 82, there's a level curve for 82 degrees. There's a level curve for 67 degrees. It's just that visually, would putting in all those lines help us? It'd be a little overwhelming. So we put in, based on your judgment really, the level curves that you want. And then you sort of make visual judgments off of that. And of course, x, y, and z can represent any quantities in any real-world application. We'll often talk about height because we're talking about the graph with z on the vertical axis. But remember that z could be x, y, and z could represent anything. Okay. So now I want to take a moment to talk about going back and forth between the surface and its level curves. So here's a function. Z equals the square root of 64 minus x squared minus y squared. What does the contour map look like? Okay. Well, first of all, what is the surface? The surface is going to be a sphere. So we already saw this for radius 3. So what's the radius of this sphere? The radius of the sphere is going to be 8. So now, right. So we're looking at level curves, which remember are z traces. So z is a constant. But first I want to think about this graphically. Where are the level curves? So, or what are the, first of all, what are the shapes of the level curves?
Circular.
If you take slices through the sphere, you're going to get circles. But now, what do these circles look like? So if you just take a slice at the z equals 0, the xy plane, you're going to get a circle radius 8. You get the full circumference, you get the full radius, full circumference of the circle. What happens if you go up higher? You're going to get smaller circles. But how are those contour curves spaced? What happens as you go z equals 1, z equals 2, z equals 3? What happens to the contour lines? They're all circles, but what changes? So the radius changes, but it doesn't change uniformly. Well, it changes in this way. So notice that to get from, to get from z, when you go z equals 0 to z equals 1, the radius doesn't change that much. When you go z equals 1 to z equals 2, the radius doesn't change that much, but it doesn't shrink that much, but shrinks a little bit. By the time you're going from z equals 6 to z equals 7, the way you're taking a slice, the circle is shrinking tremendously. Now, what quality is it about the surface that changes to what extent your contour lines are sort of running away, are changing quickly or not? Yeah.
Towards the top, the tangential planes are a lot more level.
It's flatter, exactly.
I like
So over here, when z equals near the top of the surface itself is a lot flatter. So when it's flat, when you change from z equals 6 to z equals 7, there's your contour line moves, your level curve moves a lot. But down here, when you go from z equals 0, z equals 1, z equals 2, the surface is very steep. So z can change a lot without the contour line moving that much in terms of where it is in the domain. And this is an idea that we're going to revisit a lot. So notice that the steepness of the surface affects the arrangement of the contour lines. And this is something that we're going to explore a lot. So you don't have to don't feel the pressure to understand it all right now. We're going to come back to this a lot. Okay. So you can also look at this. You can also think about the curves algebraically. So from the equation, level curve just set c equal to a constant c. So c equals the square root of 64 minus x squared minus y squared. So now just solve it out. Make it look like more like an equation in x and y. So you work that out and you get x squared plus y squared equals 64 minus c squared. So you can see it's going to be a circle with radius square root of 64 minus c squared. Okay. So far, we've looked at fairly simple, straightforward objects. Things like spheres, the paraboloids, where it's just a parabola spun around. Now, in general, surfaces in 3 dimensions can be as complicated as you like, of course, as you could imagine. Just like 2-dimensional functions, but now in 3 dimensions. So, in general, to draw level curves by hand given the formula of a surface is incredibly hard. It's algebraically it's possible in these harder cases, but doesn't give simple objects, and it's easier to either use software and or to look at the graph directly. So let's take a look. So this function, z equals negative xy e to the negative x squared minus y squared. What are the x traces? What are the y traces? What are the, instead of calling them z traces, we're going to call them level curves. So there's the surface.
It's like the equation of the right angle.
So what are the x traces? What are the y traces? What are the level curves?
X traces is when x is constant.
Right. So an x trace is when x is constant. So you can see the x-axis. So suppose we're at a spot on the x-axis right there. So now draw it so that x is constant.
Draw a plane, right? Parallel to the
Right.
y plane.
So we want this plane. So what do you get? Something like that. Right. So now so notice that we're getting to more complicated surfaces now. So it's not always the x trace will not always be the same shape. I just drew one x trace. Let's look at a different one.
the x trace at the origin looks like just straight lines.
That's a great point. The x trace when x equals 0
What does that mean algebraically?
is just that.
So that means everything is zero.
Okay. And then we can also go to the other side. So what about the x trace when x equals -3? You'll wind up over here. You'll go up here. And then it's hard to see from this angle, but that part goes down and then it comes back up. So it's the same thing we had over here, but just reversed. All right. And because of the symmetry, the y traces are going to be exactly the same. I'll let you think about that. But now I want to talk about the level curves. So the level curves are absolutely fascinating. So I want to make one important point here, which is, actually, you know what? Let's draw the level curves and then I'll make the point. Let's do that. Okay. So what are the level curves? So I always say start somewhere extreme. So for example, start near the top of the graph. So remember, level curves mean we're going to be taking, whoa.
Not Professor. X was 0, y can't be 0. He said everything is 0. And the other one?
All right.
Algebraically.
Okay, so level curves. So remember that we are taking slices using a plane, a flat plane like that. So that could be the slice, let's say z equals 3, I don't know. So what's that going to look like?
Two circles.
Right. So that slice, that plane slice, will give you a piece. Well, let's call those two mountains. It'll give you a little piece of the first mountain, a little piece of the second mountain, and they're not exactly circles, but they're kind of circle-ish. So that slice is going to give you something over here and something over here. So when z equals, let's say 3, you get that. What about, excuse me, what about when z equals 2? Something similar, but the circles will be bigger. Down here, they'll be there. Okay. Now as we go down, you're going to get a bigger circle and a bigger circle. And as you go further down, what's going to happen? Yeah. You can see that somehow these circles are going to merge in some way because the circles are getting closer and closer together. Now what happens if you take slices for negative z values? What are you going to get? So now it might be hard to see from this angle, but there's one valley over here, and there's also a valley in the back. So this shape has some kind of symmetry in that way. So here I'm using Mathematica, and I generated this picture. And so now that I've got the picture live in the software, now we can play with it.
Is this the e to the x one? E to the y squared? Is this the one we've been discussing?
Yeah.
This is the same. This is
There should be
the.
a hole. There should be a hole in the center.
There at 0, 0, 0, there should be like a discontinuity.
It is
the same graph.
At 0, 0, 0.
Okay.
Hold on. We won't see because the
Okay. So what you can also do is you can look at it from the top or the
Why
bottom.
don't we see a hole?
Because you won't be able to see it one point. There's no radius. These movements you won't be able to see.
So we can see that for z equals positive values, you get these. Well, they're not quite circles, but they're these loops. And then for z equals negative values, you also get two loops, but then you get them sort of in the opposite two quadrants. So there's got to be some kind of changeover when z goes from positive to negative, or in other words, when z equals 0. And to see what's actually happening, we can look at the actual contour map. So I'm going to mark this. So notice that from the original graph, when x and y are positive, it's below. So this is for, so here we have z less than 0. Here you have z less than 0. This gives you z greater than 0. So actually, you know what? And this one is z greater than 0. So for example, what you have is, let's see. So this is like -10, -9, -8, blah, 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 all the way to -2 and -1. Sorry, that one was positive. My bad. Excuse me. I was thinking about this one. So this is... So you've got, say, -10, -9, -8, blah, 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 all the way to -2, -1. Okay? And then for the positive one, you've got, this is 1, 2, 3, 4. And as you climb in height, your loops are getting smaller and smaller. 5, 6, blah, blah, blah. Okay. So now you have to confront the interesting idea of what's happening when z equals 0. Now, it's possible to see it on the graph, but it's a little tricky. You can also look at it on in the function. So when z equals 0, what has to be true? Either x or y has to be 0. So that tells you exactly what the contour, what that level curve looks like. That gives you this one. Or they can both be 0, sure. So that's the curve for z equals 0. So notice that we just learned something from the contour map, which we learned a couple things. First of all, a contour map, unless it's labeled, can't tell you which ones are positive and which ones are negative. So you have to sort of look at the surface a little bit and refer back and forth to figure it out. So imagine that we were going to sort of stack this into the surface. You'd have to realize that over here z is less than 0, so in a sense they stack downwards. And over here z is greater than 0, so in a sense they're stacking upwards, if that makes sense, in order to make those hills or those valleys. And second of all, we learned that it seems really weird, but you can have level curves that aren't loops. You can have like level curves where it looks like it's making a cross, an intersection. Okay. So there's a lot more to learn about level curves and these contour maps. So one comment that I want to make is that x traces and y traces are a lot simpler than level curves. And the reason for this is the following. Z, at least for what we're talking about right now, anyway, z is a function of x and y. So if you just turn, for a y trace, if you turn y to a constant, or for an x trace, you turn x into a constant, you have z is a function of y, or z is a function of x. So those traces will just look like functions. Simple. But what happens when you take z traces, or in other words, level curves? No reason to think it's a function. And in fact, we see here, we know it's not a function. The very first level curves that we got were these two loops. Not even remotely a function. You wind up with something like k equals -xy e to the -x squared -y squared. That's not a function. You can just see it from the expression, and you can see it when we just take the slice and draw that level curve. You get these two loops. So the level curves themselves are going to be very complicated. So connecting the graph to the level curves can be challenging. It's interesting. It's also important.
How can we tell